In the third and final part of Precalculus Lesson 14, we continue graphing rational functions. We'll be introducing slant asymptotes here. This lesson is from section 3.3 in the College Algebra textbook. We start by looking at a slant asymptote. It would be this dashed line that you're seeing here. A slant, sometimes called oblique asymptote, as you note from the graph, as our graph heads to the right, the graph is getting closer and closer to that slant asymptote. Same as the graph heads to the left, it approaches the slant asymptote. To determine if we have a slant asymptote, we have a rational function r of x equals p of x over q of x. If the degree of p is exactly one more than the degree of q, then we do have a slant asymptote. And the way that we would find that slant asymptote is to divide p of x by q of x and find the quotient. And we'll do that in just a minute here. First, let's look at some functions. F of x equals 3x plus 2 over 7x squared minus 5x plus 3. Note that the degree of the numerator is 1. The degree of the denominator is 2. Whenever the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote. For g of x, which has a leading term of 3x cubed in the numerator, a leading term of x squared in the denominator, the degree of the numerator is 3, the degree of the denominator is 2, the degree of the numerator is exactly one more than the degree of the denominator, so we do have a slant asymptote in this case. H of x has a leading term of 5x to the fifth in the numerator and a leading term of x cubed in the denominator. The degree of the numerator is 2 more than the degree of the denominator. So this function will have neither a horizontal nor a slant asymptote. And a graph will have either a horizontal or a slant or neither. There are only those three choices as far as asymptotes. We're going to find the slant asymptote of the function g of x that we just looked at. So we take 3x cubed minus x squared plus 4x minus 1 over x squared minus 2x plus 3. To find that slant asymptote, if possible, I would use synthetic division. It saves some time. But noting that I have a quadratic in the denominator here, we will need to use long division. So let me just change colors here. And so we have x squared minus 2x plus 3. We're dividing the denominator into the numerator of 3x cubed minus x squared plus 4x minus 1. So 3x cubed divided by x squared would give us 3x. 3x times x squared minus 2x plus 3 gives us 3x cubed minus 6x squared, and then plus 9x. We subtract to get 5x squared minus 5x, bring down the negative 1. Then x squared goes into 5x squared 5 times, so I add 5 to the quotient here. 5 times x squared minus 2x plus 3, we get 5x squared minus 10x, and then plus 15, subtracting, results in 5x minus 16. This is the remainder, and what's kind of nice about determining slant asymptotes is we can ignore the remainder. All we're interested in is this quotient. And so what I've found is our slant asymptote, which is a line, needs to be written as a line, is y equals 3x plus 5. All right, let's go on to graphing the rational function r of x equals x squared over x minus 2. The first thing I'll look for is the domain, and you can see here the domain would exclude x equals 2. All other x values would be included, so our domain would be negative infinity to 2, union 2 to infinity. For holes in the graph here, there are no common factors between the numerator and denominator, so I can say there are no holes. X-intercepts. for x-intercepts, we set y equal to 0, and we can see setting r of x equal to 0 here would result in x squared being equal to 0, or x being equal to 0. That would give us an x-intercept of 0, 0. Well, when we look for our y-intercept, already knowing that 0, 0 is our x-intercept, it would have to be the y-intercept as well, since our graph could only cross that y-axis at one point. Now, vertical asymptotes, there's one factor of x minus 2 in the denominator. We set that factor equal to 0 to get a vertical asymptote x equals 2. The slant asymptote, I see that the degree of the numerator is 2, the degree of the denominator is 1. So indeed, we do have a slant asymptote here. I would divide x minus 2 into x squared. I'm going to use synthetic division here. So x minus 2 into 1 times x squared plus 0x plus 0, bring down the 1. 2 times 1 is 2, 0 plus 2 is 2, 2 times 2 is 4, 0 plus 4 is 4. I find that my quotient is x plus 2. Ignore the remainder. Our slant asymptote is going to be y equals x plus 2. Now we'll start graphing. We start by plotting the information we have so far. We have an intercept of 0, 0. We have a vertical asymptote, x equals 2. And let's plot that slant asymptote. Well, to plot the slant asymptote, I'm going to determine some points that would be on my slant asymptote. So we're graphing a line basically at this point. So to find points on the slant asymptote, if I plug in an x value of -2, I get a y value of 0. If I plug in an x value of 0, I get a y value of 2. So the points -2, 0 and 0, 2 will be on the slant asymptote. From there, we just draw a dashed line through those 2 points, and we have our slant asymptote. So the next thing we want to do is we want to graph the function. Well, I don't know any actual points on the graph that are either above or below the x-axis, so I'm going to have to plot one somewhere. So notice remember that we need to find a point between x-intercepts and vertical asymptote. So I need to find a point right in this region between x equals 0 and x equals 1. What I'll do is I'll look back at my function and I'll use that function to find a point that would be on the graph. So for an additional point to plot, let's let x be equal to 1 here, and then we would have 1 squared over 1 minus 2. That would give us a y-coordinate here of -1. And so I'm going to plot the point 1, -1. Then we could see to the right of the x-intercept, until we get up to the vertical asymptote of x equals 2, the graph is below the x-axis, approaching that vertical asymptote. I'm going to look again at my point of 0, 0. There are no more vertical asymptotes or x-intercepts to the left of that point. So all I need to do is to determine what happens at that point of 0, 0. Well, that point of 0, 0 came from our numerator here. So from x squared. So note that we have a multiplicity of 2 on that 0, meaning the graph is going to simply touch and bounce at that point. And then as we go to the left, our graph will be approaching the slant asymptote like so. Now we have a little bit more graphing to do. Let's look again at our vertical asymptote here. So our vertical asymptote, x equals 2. If we want to figure out what's going on to the right of that vertical asymptote, notice to the left, our graph is approaching -infinity. The factor in the denominator from which I got the vertical asymptote is raised to the first power. That's odd. That means that to the right of the vertical asymptote, my graph is going to be headed towards +infinity. The graph will look something like this. And again, as we head to the right here, we're going to be approaching that slant asymptote. So here we have our graph. Now let's graph another slightly more complicated function. F of x equals x cubed minus 3x squared minus 4x plus 12 over x squared minus x minus 2. To find the domain, we'll need to factor that denominator into x minus 2 times x plus 1. Okay, and I'll factor the numerator in a minute here. So our domain is going to exclude x equals 2 and x equals negative 1. And so what have we got going on here? Well, our domain would be, what is included here would be negative infinity to negative 1, union negative 1 to 2, union 2 to infinity. Okay, this is our domain. Before going on, let's look for holes. So to find holes, I'm going to factor x cubed minus 3x squared minus 4x plus 12. Okay, I'll use factoring by grouping here. If factoring by grouping didn't work, I would need to resort to finding potential rational zeros like we've been doing. So factoring by grouping from x cubed minus 3x squared, the greatest common factor would be x squared. So I have x squared times x minus 3. From negative 4x plus 12, I can pull out a negative 4. I have negative 4 times x minus 3. Then we would have x squared minus 4 times x minus 3. And I can see that x squared minus 4 further factors into x minus 2 times x plus 2. And then we have times x minus 3. So do we have any common factors between the numerator and denominator? Well, it looks like x minus 2, doesn't it? So when I'm finding holes, I'm going to rewrite f of x as x plus 2 times x minus 3 over x plus 1, noting that x cannot be equal to 2. Okay, so we rewrite our function. What's happening at 2, if it's not included in our graph, that is where we'd have a hole. So at x equals 2, and to find the y value there, I would go back to this simplified function here. And so if I plug in an x value of 2 there, I'd have 2 plus 2, or 4, times 2 minus 3. 4 times negative 1 would give me negative 4 over 2 plus 1, or 3. So we would have the hole on our graph at the point 2, negative 4/3. All right, moving on. Now we're going to leave our function rewritten like so. I'm going to show both the factored form here and of x minus 3 times x plus 2 over x plus 1, and the expanded version x squared minus x minus 6 over x plus 1. Different things that we're trying to find here work better for one of those two different versions. For example, x-intercepts. If I look at this factored version right here, I can see that my x-intercepts would occur when y is equal to 0, or in this case, when x minus 3 equals 0, or when x plus 2 equals 0. That gives me x equals 3, x equals negative 2 for x-intercepts of 3, 0, and negative 2, 0. For the y-intercept, we just look at this other version here. We set x equal to 0 to give us y equals 0 squared minus 0 minus 6 over 0 plus 1. We get negative 6 for a y-intercept of 0, negative 6. Then we look for asymptotes. The vertical asymptote we can see in either one of these two versions we would set x plus 1 equal to 0 to give us x equals negative 1. And we can see the degree of the numerator is 1 more than the degree of the denominator, so we do have a slant asymptote here. To find that slant asymptote, I'm going to use the second version here, and I would divide x plus 1 using synthetic division into 1 times x squared minus 1 times x minus 6. Bring down the 1. Negative 1 times 1 is negative 1. Negative 1 plus a negative 1 would be negative 2. Negative 1 times negative 2 is 2. We get a remainder of negative 4, which we can ignore. We see our quotient here would be x minus 2. So our slant asymptote will be y equals x minus 2. Now, moving on to graphing, we put down all the information we found so far. And I'll go ahead and plot the x-intercepts of -2, 0 and 3, 0, along with the y-intercept of 0, -6, and the whole. You can see we plotted the whole here, 2, -4/3. Okay, so to find the vertical asymptote, or to plot the vertical asymptote, we just sketch a dashed line here, x equals -1. The slant asymptote, remember we need to plot a few points to draw this line as our dashed slant asymptote. So for some points in the slant asymptote, we can plug in an x value of 0 to give us a y coordinate of -2. We can plug in an x coordinate of 2 to give us a y coordinate of 0. And then I'll go ahead and plot these 2 points on the slant asymptote, connect the points with the dashed slant asymptote. And now what have we got going on here? Well, I can see to the right of, let's see, to the right of, well, between my vertical asymptote and the x-intercept here, between those two, I can see the graph is below the x-axis, right? We have a y-intercept at the point 0, -6. So let's go ahead and fill in that region. So between x equals -1 and x equals 2, the graph's below the x-axis. It kind of passes by the hole and then it goes through the y-intercept. To the right of to the right of 3, 0, my x-intercept 3, 0, are we above or below the x-axis? Well, let's look at where that 3, 0 came from. It came from this factor of x minus 3 that's raised to the first power. So our graph is going to cross at that point, and indeed it will head on up, approaching that slant asymptote. Now, to the left of the vertical asymptote here, between x equals -1, where we have between x equals -2, where we have another x-intercept, and between x equals -1, where we have a vertical asymptote, we don't know what's going on, but I think we can figure out what's going on fairly easily. Let's look where that asymptote of x equals -1 came from. So notice it came from this denominator. It has a power of 1, which is odd. So if to the right of the vertical asymptote, my graph is headed down, it's going to be heading left to the left of the vertical asymptote. An odd power means we're going to be changing directions. What's happening at x equals -2? -2, our x-intercept of -2, comes from the factor x plus 2 raised to the first power, an odd power in the numerator. So our graph is going to cross at that point. It will head on down and approach the slant asymptote. All right, there we have it. So try on your own number 3. Find the slant asymptote of the rational function r of x equals -3x squared plus 11x minus 12, or I'm sorry, 11x minus 11 over x minus 4.